Hello there. Welcome to Just About Space, your quiet window into the cosmos. Tonight, we're letting go of the noise, of the weight, of the frantic spinning of our little lives, and instead, we're floating outward, into silence, into symmetry, into a question that sounds simple, but ripples through every star, every atom, every breath you've ever taken. Why is space so balanced? Because it really shouldn't be. The Big Bang was chaos, matter flying outward, energy raging in every direction. And yet, here we are. Galaxies didn't tear themselves apart. Stars didn't collapse before forming. Planets like Earth didn't just fall into black holes or dissolve into dust. Somehow, across this incomprehensible vacuum, things held together just enough, just tightly enough, just delicately enough to form gravity, galaxies, elements, orbits, atmospheres, life. This balance isn't perfect, but it's eerily close. Too much energy, and atoms wouldn't form. Too little, and the universe would have collapsed in on itself. The speed of light, the strength of gravity, the mass of an electron. Why are these numbers so precise? Tonight, we're not looking for a definitive answer. We're looking to explore, to wonder, to fall asleep beside the question. Close your eyes if you like, and drift with me now into the strange, elegant tension that holds our universe together. As we ask, how did space know to be so balanced? Imagine this. You are not you. You are everything and nothing all at once. You are not standing, sitting, or floating. You are the singularity, a point so small it has no width, no height, no up or down, just unimaginable energy, waiting. And then, it happens. In a flash so quick no time can contain it, you explode, not in a bang like a cannon or a bomb, but in a release of space itself. Time begins. Matter unfurls, forces emerge, and you, the universe, expand, not into space, but creating space as you go. But here's the thing, that explosion could have been chaos. 1 billion possibilities, and nearly all of them lead nowhere. Too much energy, and everything rips apart before anything can form. Tilted even slightly the wrong way. And this script doesn't exist because neither do you. And yet, it balanced. Somehow. We call it fine-tuning, and it starts here with what's known as the cosmic coin toss. Because in the earliest moments after the Big Bang, we're talking trillionths of a second, the universe had to choose its rules. Did it want gravity to be slightly stronger, then stars would collapse in on themselves? Did it want the strong nuclear force to be a bit weaker, then atoms wouldn't bind? Did it want more antimatter than matter? Well, then we'd have nothing at all. Instead, it picked a path so absurdly narrow that it defies logic, a universe that isn't perfectly balanced, but balanced enough. And that sits just the start. Physicists refer to this phenomenon as symmetry breaking. The universe wasn't built like a Lego set. It was a mess, particles flinging out, forces unfolding, dimensions twisting open like petals in a black blossom. But instead of falling apart, it snapped into shape. 4 fundamental forces emerged. Gravity pulling everything inward. Electromagnetism. The strong nuclear force. The weak nuclear force. Each of these forces could have been stronger, weaker, or unstable altogether. But they weren't. They settled into perfect ratios, like an orchestra tuning itself without a conductor. Now you're wondering, was this luck? Was it necessity? Or something else? Some theories suggest a multiverse, where infinite versions of space exist, each with its own rules. Most of them are dead. No stars, no matter, no balance. But a few rare ones, like ours, strike just the right chord. Others propose something bolder, that the universe is self-selecting, that only those universes capable of containing observers like you are the ones that can be observed in the first place. A strange chicken and egg loop of cosmological logic. But even if these theories hold truth, They don't change the awe, because here we are, in a universe that teetered on a razor's edge and landed just right. Not too hot, not too cold, not too fast, not too slow. The cosmic version of flipping a coin 1,000 times and landing heads every single time. And no one really knows why. That sip's what keeps physicists up at night, and what helps the rest of us fall asleep, because there sips something strangely comforting about this. The idea that your very existence is the result of near impossible balance, that stars formed not because they had to, but because everything somehow lined up just enough. The atoms in your body, forged in ancient stars. The gravity keeping you tucked into bed, steady and unyielding. The light bouncing off your walls, humming at precisely the right frequency. All of it only works if the cosmic coin toss comes up just so. You don't need to solve this mystery tonight. You just need to feel it. Let it wash over you. Let it quiet the noise of the day. Because balance isn't just something the universe once found. It's something it keeps practicing over and over, in every orbit, every breath, every ticking of time. So as you drift into sleep, just remember, you are not a mistake. You are not randomness. You are the soft echo of a cosmic choice, made in silence, made in symmetry, made in a fraction of a second when everything could have gone wrong, but didn't. And now, you rest within that balance. You never notice gravity until it stops working. And yet, without it, your lungs wouldn't know how to breathe. Your feet wouldn't know how to stay planted. The Earth wouldn't know how to hold itself together, let alone orbit the sun. But here's the haunting part. It's by far the weakest of the four fundamental forces. Imagine this. You lift a paperclip with a tiny magnet. In that moment, electromagnetism has defeated the gravity of the entire Earth. That's how weak gravity is. And yet it reigns supreme across the universe. Why? Because gravity only pulls. It doesn't cancel itself out like electricity does. There's no anti-gravity charge to balance it. And over vast distances, that tiny pull accumulates, snowballs, gathers mass, until it becomes powerful enough to collapse stars into black holes and bend light itself. But here's the riddle. Physicists can't solve why is gravity so weak in the first place. It's called the hierarchy problem, and it's one of the biggest puzzles in modern physics. The gravitational force is about 10 circumflex 36 times weaker than the electromagnetic force. That's a trillion. If gravity had been just a little stronger, stars would have burned faster, collapsed sooner. If it were even weaker, matter might never have clumped together at all. So, is gravity holding back, or is it leaking? One theory suggests that gravity isn't weak, it's just spread out. According to models of extra dimensions, gravity may be diluted across higher dimensional space. Imagine a speaker playing music in a closed room, loud and clear. Now imagine that room has a hidden door to another room. Some of the sound leaks through and the volume drops. If gravity is leaking into other dimensions, what we feel here is just a faint whisper of its true strength. But we don't still know, not yet. And still, even in its gentleness, gravity is a master builder. It gathers clouds of hydrogen in the void and squeezes them until fusion ignites. That's how stars are born. It stirs galaxies into spirals, keeps moons dancing around planets, guides asteroids across billions of miles with eerie precision. It's even the reason time itself is flexible. Einstein taught us that gravity isn't just a force. It's the curvature of space and time. Where there's mass, space bends, and where space bends, time slows down. So when you lie down and feel the pull of your mattress beneath you, you're not just feeling weight. You're feeling the curvature of space-time itself. You're being held in place by the shape of the universe. And then there are black holes. Gravity sets final performance. Take a star, say 10 times the mass of our sun. Let it burn through its fuel. Let it collapse inward, with no pressure left to hold it up. Gravity takes over. And it doesn't stop. It pulls everything, atoms, light, even the concept of location, into a point of infinite density, a singularity. Around this singularity forms the event horizon, a boundary beyond which nothing returns, not because it's a wall, but because the path forward always leads deeper in. To escape, you'd need to travel faster than light, and that's not allowed. But black holes aren't just graveyards. They may be gateways. Some theories propose that black holes could contain bridges to other parts of the universe, or even other universes. These theoretical passages are called Einstein-Rosen bridges, or more popularly wormholes. They're purely speculative, but tantalizing. Could gravity not only collapse stars but stitch together realities? And then, beyond black holes, there's dark matter, the ghost we can see. Galaxies spin too fast. Based on what we can observe, they should fly apart, but they don't. Something is holding them together. An invisible hand. We call it dark matter, but that's just a label for ignorance. We don't know what it is. We only know it's affected by gravity, that it's 5 times more abundant than normal matter, that it passes through you every second, unnoticed. And gravity is our only clue. Bastet's poetry in that. And yet it works. It lets Earth hug its atmosphere, it lets water fall, it lets the moon tug gently on our oceans, giving us tides, a rhythm older than writing. So tonight, while you rest, know that you are gently tethered to the world by this invisible sculpture, that your body and the planet are in quiet conversation, exchanging force, shape, and time. You are being held. Not tightly, not cruelly, but consistently, faithfully, as stars are held, as galaxies are held. And whether gravity is leaking into higher dimensions or tuned just right, by some deeper principle we don't yet know, it is working. Softly, steadily, invisibly. Because in a universe that seems so chaotic, gravity is the constant hum in the background, the quiet answer to every question that begins with, why did and set everything fall apart? Hello again. Still awake? Good, because now we ask something even more unnerving than where the universe came from. We ask, why does it follow rules? Not human rules, not rules made by kings or scientists or textbooks, but fundamental laws, invisible, unchanging patterns that everything seems to obey. Why does light always travel at the same speed? Why does energy never vanish, only change form? Why do particles follow probabilistic patterns and not pure chaos? You are floating in a cosmos governed by laws that never took a vote. They were never written down, and yet every electron, every planet, every black hole obeys them without rebellion. It's not just that the universe has order, it's that the order seems built in. In vacuum, it's always the same 299,792,458 meters per second. No more, no less. Doesn't matter if the light comes from a flashlight, a quasar, or the remnants of the Big Bang. Doesn't matter if you're running toward it or away from it. It doesn't speed up or slow down for you. Einstein showed that this constancy is what warps space and time. But why is it constant? Why that exact number? Why not a little faster? Or slower? No one knows. It's just one of the given values. The universe has a handful of these called fundamental constants, numbers baked into the fabric of reality. The gravitational constant, the charge of the electron, Planck's constant, the mass of the proton. These values are like the knobs and dials behind the curtain of existence, and somehow they've been set to just the right levels for atoms to form, stars to ignite, and life to emerge. This brings us to the infamous fine-tuning problem. If even one of these constants had been slightly different, if gravity were stronger, or the strong nuclear force were weaker, we might not be here. Stars wouldn't last long enough to forge complex elements. Matter might never clump. Chemistry itself might be impossible. Now, you might say, well, of course, they're set just right. We're here to observe them. That's called the anthropic principle. And it's one explanation, but it doesn't satisfy everyone. Some physicists suggest that these constants are the result of deep mathematical inevitability, that the laws couldn't be any other way. Others propose a multiverse, an uncountable number of universes, each with different laws and constants, and we just happen to live in the one where everything works. But here's the quiet, unsettling truth. We have no idea where the laws of physics come from. They didn't emerge from particles. They govern the particles. They didn't evolve. They didn't mutate. They don't seem to depend on time or location. The law that governs how gravity works, Newton's inverse square law, works just as well in Andromeda as it does in your kitchen. They are, in a way, outside the universe, or at least outside everything inside it. And yet, these laws are expressed in mathematical form, in equations that can be written down on paper, coded into a simulation, or described in clean, elegant symbols. So here's another mystery. Why is the universe so mathematical? It didn't have to be. Nature could have been raw, messy, chaotic, full of exceptions and contradictions, but instead it's full of symmetry, consistency, and logic. Mathematician Eugene Wigner called it the unreasonable effectiveness of mathematics. It's as if the universe wants to be understood, as if the laws are not only present but expressible in the language of math, a language we somehow evolved to speak. But here zips a darker, more humbling thought. Maybe we're just seeing the parts that can be written down. Maybe the laws we've discovered, like relativity and quantum mechanics, are just the surface crust of a deeper, weirder structure we don't yet comprehend. Think about it. Newton's laws seemed perfect, until Einstein came along and said, well, almost. Einstein's relativity seemed final, until quantum theory cracked the neatness wide open. Now we live in a world where quantum particles disobey intuition, and general relativity refuses to cooperate with quantum field theory. It's like we're looking at a masterpiece through a keyhole. And yet, what we do see is enough to launch rockets, split atoms, predict eclipses, simulate weather, and create artificial intelligence. The laws hold. They don't care whether we believe in them. They don't change when you stop looking. They don't take your confusion personally. And here's the most paradoxical part. Even chaos follows laws. When you simulate a chaotic system, like a hurricane, a turbulent ocean, or a population of predators and prey, it looks unpredictable, but it still follows rules. It's not randomness. It's sensitive dependence on initial conditions. The famous butterfly effect. The laws remain, even if the outcomes spiral beyond comprehension. The laws are the skeleton of reality. Everything else, stars, galaxies, dreams, poems, is just skin, breath, and noise layered on top. So as you drift tonight, ask yourself, who wrote these laws? Were they forged in the Big Bang? Were they always there waiting? Are they signs of a deeper intelligence or just blind logic playing itself out? Is math the language of God, or just the only language we've learned to listen in? No one knows. But here's what we do know. The laws haven't failed us yet. Not when apples fell from trees. Not when planets circled stars. Not when telescopes peered back 13 billion years and saw light still obeying the rules. Tonight, you are governed by those same laws. Your breath, your heartbeat, the way your atoms hold together, it all unfolds according to quiet rules written into the void. You don't need to memorize them. Just feel them. They are already working. Hello again, still with me. Let's talk about something that doesn't talk back. Something vast, invisible, and persistent. Something that isn't made of matter or light or time. Something that doesn't burn, doesn't fall, and doesn't collide. It doesn't make a sound. It doesn't leave a trace. And yet it is slowly, very slowly, pulling everything apart. They call it dark energy. and no one knows what it is. Here sits what we do know. In 1929, Edwin Hubble looked at distant galaxies and noticed something strange. They were moving away from us, and not just moving. The farther away they were, the faster they were receding. This wasn't just a local fluke. It was everywhere. The universe wasn't static. It was expanding. That was the beginning of the end for the old steady-state models. Suddenly, the cosmos looked more like a balloon than a clock, always stretching, growing, cooling. For decades, scientists assumed that this expansion must be slowing down. Gravity, after all, pulls things together. Surely the combined mass of all stars, dust, gas, and dark matter would eventually tug the universe back inward, maybe even collapse it. But in the late 1990s, two teams of astronomers studying distant supernovae found something astonishing. The expansion of the universe wasn't slowing down. It was speeding up. That's like throwing a ball in the air and having it soar faster the higher it gets. It doesn't make intuitive sense, but that's what the data showed. Something is pushing the universe outward, faster and faster, and that something was given a placeholder name, dark energy. It is estimated to make up about 68% of the entire energy content of the universe, and yet it can't be seen, touched, or directly measured. It doesn't clump like matter. It doesn't curve space-time the way mass does. It behaves more like a property of empty space itself, a gentle pressure that increases with distance. And that sips the haunting part. Dark energy increases with distance. The more space you have, the more of it there is. It doesn't dilute as the universe expands. It grows with the expansion. So the more space is created, the more dark energy you get, which then creates even more space. A runaway effect. That means we're living in a universe with a built-in accelerator pedal and no brakes. Well, on a long enough timeline, galaxies will drift so far apart that light from one can never reach another. Stars will die, black holes will fade, and the sky will grow empty and cold. Not with a bang, but with distance. This future is sometimes called the Big Freeze, a time when the cosmos becomes a vast silent void, where even atoms might someday dissolve into radiation. But that's billions upon billions of years away. Tonight, it's just a quiet pressure, a hush behind the stars, pushing everything outward with infinite patience. Theories about what dark energy actually is vary. Some physicists believe it's a cosmological constant, a fixed value Einstein once introduced and then discarded in his equations. Others suspect it may be the result of quantum vacuum fluctuations, tiny momentary blips in energy that appear and disappear in empty space. Some believe dark energy is a new kind of field, something like the Higgs field, but even more elusive. And then there's the most speculative theory of all, that dark energy is not a thing, but a sign that our models are incomplete, that gravity might behave differently on cosmological scales, that the universe may be hiding dimensions, folds, or corrections we haven't yet glimpsed. But in the meantime, it's here, in every direction, in every galaxy, in every stretch of nothing. It is, quite literally, the dominant force in the universe. And yet, you Sib never felt it. It doesn't weigh you down. It doesn't warm your skin. It doesn't make your bones creak or your hair stand on end. It is quiet, cold, constant, and it tells us something both beautiful and terrifying. The universe is not just expanding, it is accelerating into solitude. In the far future, this acceleration means entire galaxies, even clusters of galaxies, will pass beyond our cosmic horizon. Their light will never reach us no matter how long we wait. The observable universe will shrink, even as the real universe continues to expand. It's like watching islands vanish over the curve of the ocean, not because they sank, but because the sea itself grew faster than your boat could follow. But here sits a gentler thought. Right now, you live in a moment when the night sky is still full. In a way, this is the most visible the universe will ever be. So as you lie in the dark tonight, remember you are floating in a universe full of silence. Yes, but also full of light that still reaches you, stars that still shine in defiance of the cold, and questions that still hum beneath every empty space. Dark energy does not shout, it does not sparkle, it does not beg for attention, it simply expands. And one day it will have all the room it wants. But tonight, you still have stars. And that sip's enough. You've heard the phrase, everything is connected, right? Symmetry is what keeps the universe from falling apart. Let's take a step back. Imagine tossing a ball into the air. The laws that govern that motion, gravity, inertia, momentum, don't care where you're standing. They don't change if you move 5 feet to the left. That's translational symmetry. The rules of physics stay the same no matter where you are. Now imagine watching that same ball toss tomorrow instead of today. Still works, right? That's time symmetry. Physics doesn't care what day it is. These symmetries aren't just philosophical ideas, they're the backbone of physical law. In fact, in the early 20th century, a mathematician named Emmy Noether proved one of the most important theorems in all of science. For every symmetry in nature, there is a corresponding conservation law. Translation in time, that's why energy is conserved. Translation in space, that's why momentum is conserved. Rotation symmetry, that's why angular momentum is conserved. That's not just elegant, it's terrifyingly precise. But this idea goes deeper, much deeper. Symmetry governs particles. Symmetry dictates forces. Symmetry defines the very fabric of reality. Take the standard model of particle physics, our best framework for understanding how the smallest building blocks of reality behave. It's based almost entirely on gauge symmetries, abstract mathematical rules that dictate how particles interact. Think of it like this. You're allowed to rotate a certain property of a particle, like its charge or spin, and the equations still hold true. These aren't visual symmetries like shapes. They're more like internal dials hidden in the math. But they're essential. Without these symmetries, particles wouldn't behave predictably. Forces wouldn't exist. The universe would have no consistency. But here's where it gets weird. Symmetry breaking is just as important. In the early universe, right after the Big Bang, things were more symmetrical than they are now. Forces that seemed separate today, like electromagnetism and the weak nuclear force, were once unified under a single symmetric rule. In fact, the Higgs field, which gives mass to fundamental particles, exists because of spontaneous symmetry breaking. It's not that the symmetry is gone, it's just hidden, like a coin that lands on heads, breaking the symmetry of possibility, even though both outcomes were equally valid before. This breaking is what gives the universe texture. There's even a theory that the universe might contain supersymmetry, an unconfirmed idea that every known particle has a superpartner. If true, it would solve a lot of problems in physics, like the nature of dark matter and the unification of forces. But we haven't seen these superpartners yet. Maybe they're too heavy. Maybe the symmetry broke more violently than we expected. And speaking of breaking, you know how matter and antimatter are supposed to be created in equal amounts. That's what symmetry would demand. But we're here, and clearly made of matter, not antimatter. So something broke that symmetry too, and no one fully knows how. It's one of the deepest open questions in physics. Why does anything exist at all, instead of everything cancelling out? Now zoom out. Symmetry isn't just a quantum rule, it governs galaxies. It governs orbits. The reason Earth doesn't spiral into the sun, that's conservation of angular momentum, a symmetry in space. The reason stars form disks, gravity plus the same principle. Symmetry governs beauty too. We find symmetrical faces attractive, symmetrical music satisfying, symmetrical patterns soothing. Maybe because symmetry is a kind of whisper, a suggestion that things make sense at a deeper level. But even that comfort has a shadow. When symmetry breaks, we get complexity, we get form, we get change. So the very imperfections in the universe, the tiny asymmetries, are what allow it to exist at all. Tonight, think about this. Every step you take conserves momentum. Every breath, every heartbeat operates inside a quiet ballet of forces that don't betray you. Not because the universe cares, but because the universe is symmetrical. Enough. There's something humbling in knowing that particles obey rules older than stars, that deep down there are balances being preserved, balances you never see, never feel, but which allow you to see and feel anything at all. The universe may not have a purpose, but it has form, and form begins with symmetry. You're floating now, slowly, calmly, somewhere between Mars and Jupiter. There is no air here, no sound, no scent, but everything around you is made of potential. Invisible rivers of molecules flow across the galaxy. Space, it turns out, is not empty. It's not sterile. It's not even lifeless. It's sex chemical. Let's begin with one fact that continues to surprise even the most seasoned astronomers: organic molecules. The building blocks of life are everywhere, not just in laboratories or biological cells, but drifting quietly in interstellar clouds, clinging to icy comets, forming on dust grains that wander light years between stars. Organic molecules are molecules that contain carbon and are often associated with life. But life doesn't need to be present for these molecules to form. In fact, we found things like amino acids, nucleobases, formaldehyde, and even ethyl formate, the chemical that gives raspberries their smell, in regions of space where no planet has ever formed. The origin? Interstellar dust clouds, cold, dark regions of space where molecules condense on the surfaces of icy dust grains. These grains act like tiny chemical factories. Hydrogen sticks, carbon monoxide sticks, nitrogen sticks. We're talking prebiotic chemistry on a cosmic scale, not in one place, but in hundreds, thousands, maybe millions of star systems. One such place is the Taurus molecular cloud, about 450 light-years away. It's rich in carbon-based molecules. Scientists using radio telescopes have detected molecules like cyanopolines there, long chains of carbon and nitrogen atoms, considered critical in early chemical evolution. These are ingredients for life, showing up uninvited in places too cold, too distant, too ancient to support biology as we know it. So, what does that mean? It means that the chemistry of life is not unique to Earth. The seeds of biology are baked into the galaxy itself. Life, in chemical terms, is not an anomaly. It may be an emergent property of the cosmos. Even Saturn's moon Titan has shown signs of this interstellar chemistry. Titan is cloaked in a thick atmosphere rich in methane and nitrogen. And beneath that veil, scientists believe a hydrocarbon cycle mirrors Earth's water cycle, with methane rain, rivers, and lakes. Complex organic molecules have been detected swirling in its hazy skies. Some scientists even believe Titan may host a form of alien life, one that uses methane instead of water as its biological solvent. In 2020, researchers detected a molecule called phosphine in the atmosphere of Venus, a potential biosignature, since phosphine is difficult to make without biological processes. The claim is still debated, and it may yet have an abiotic explanation, but the mere possibility highlights a profound truth. Lifelike chemistry appears in multiple places, in multiple ways. What if life doesn't begin where it's comfortable, but where the ingredients are simply persistent? What if Earth isn't the origin point, but one node in a galactic network of life's chemistry? This brings us to the theory of panspermia, the idea that life, or at least the precursors to life, can travel across the universe on comets, meteoroids, or dust. Some scientists believe that early Earth was seeded by these interstellar travelers, bringing amino acids, sugars, maybe even primitive cells from far beyond our solar system. It sounds like science fiction, but experiments aboard the International Space Station have shown that certain microorganisms can survive the vacuum of space, the freezing cold and intense radiation, for years. The ingredients for life are durable, resilient, stubborn, which leads to a gentle but unsettling idea. Maybe the galaxy is not waiting for life to arise. Maybe it's already brewing it everywhere, not as intelligent civilizations, but as chemical stories unfolding slowly across billions of years. And maybe we're just one flavor of that unfolding, one permutation of carbon, nitrogen, water, and heat. Tonight, as you close your eyes, picture the vast lanes of the Milky Way, spiral arms not of emptiness, but of carbon chains, dusty molecules, frozen amino acids silently drifting towards something new. You are a product of those molecules. You are made of the same story that plays out in nebulae, on icy moons, and in the chemical fog of dark clouds. Life didn't rise against the odds. It may have always been part of the plan. Not the plan of a designer, the plan of chemistry. You glance at your watch. A second ticks by. But in space, it doesn't stick the same way. Time is not absolute. Time bends, time stretches, time collapses. And the deeper into the cosmos you go, the more this simple truth reveals itself. Now is an illusion. Let sex begin with Einstein, the man who cracked open the universe with a theory so bold and strange that we are still unpacking its implications more than a century later. In 1905, he published his theory of special relativity, and with it came one of the most jarring revelations in human history. Time moves differently depending on how fast you're going. This isn't metaphor. This isn't poetic. It's measurable, tested, and real. A clock on a fast-moving spacecraft will literally tick slower than one on Earth. And the faster you go, especially as you approach the speed of light, the more dramatically your experience of time diverges from those you leave behind. This is called time dilation. Here's an example. Imagine you board a spaceship capable of reaching 90% the speed of light. You travel for what feels like 1 year. When you return to Earth, more than 2 years have passed for everyone else. You've aged 1 year. Your friends have aged 2. You skipped time without ever noticing. This is not hypothetical. It's been verified using atomic clocks flown on airplanes. It's why GPS satellites have to constantly adjust their onboard clocks, because time runs differently at altitude and velocity than it does on the surface of Earth. Einstein's later theory, general relativity, introduced a new twist. Gravity affects time too. The closer you are to a massive object, the slower time passes for you compared to someone farther away. This is not intuitive, but it's been proven repeatedly. In fact, astronauts on the International Space Station age ever so slightly slower than people on Earth, and people living at sea level age just a bit more slowly than those on mountaintops. The difference is tiny, but it exists. In a way, we are all time travelers. All of us experience time just a little differently, depending on our position and motion. But the implications go deeper. If time is relative, if your now is different from someone else's, then the idea of a universal present moment dissolves. There is no single objective now that applies to everyone across the cosmos. Think about that. A star 1,000 light-years away could have exploded a millennium ago, but its light is only reaching Earth tonight. To you, that supernova is happening now, but in its own region of space, it's long over. Which moment is real? Both are, and neither. Time, it seems, is woven into the fabric of space. It curves around stars. It stretches under speed. It loops near black holes. It's elastic, not fixed. Personal, not universal. And black holes, oh, they break time entirely. This is not science fiction. This is tested theory confirmed by astronomical observations and gravitational lensing effects. It's even part of the GPS systems we use every day. It means now isn't real. It's a local phenomenon, unique to your perspective, your heartbeat, your altitude, your velocity. Someone else's now is slightly different, and at cosmic distances, wildly different. Some physicists go further. In modern theoretical physics, there are frameworks that suggest time might not even exist at all, at least not in the way we think. The universe may be fundamentally timeless, with time emerging only as a result of thermodynamic entropy, the direction in which disorder increases. In other words, the reason you remember yesterday and not tomorrow is because entropy increases in one direction. That's it. Time is not a flowing river. It's a measure of change, a narrative imposed on the universe by consciousness. Which brings us to a very strange possibility. In certain models, the past, present, and future all exist simultaneously. They're like pages in a book, fixed, eternal, all there at once. We only experience them one page at a time because our brains are wired to perceive causality. This view is called the block universe theory, a model in which time is a dimension like space, and the idea of moving forward is just our limited perspective crawling through the fourth dimension. Under this view, the future has already happened, and the past never went away. You are a four-dimensional being, stretched across space and time like a worm in an apple. You just happen to experience yourself one slice at a time. It's dizzying. It's beautiful. It's deeply unsettling. No moment is ever lost. If time is not a river but a landscape, then every smile, every failure, every moment of awe and grief you've ever lived still exists. Somewhere in the fabric of the cosmos, those moments are preserved. They didn't vanish. They're just behind you in the structure of space-time. So as you lie there now, listening to the soft hum of space, the illusion of a ticking clock dissolves. There is no now, only your now. And that's okay. In a universe where time is relative, what matters is not how much time you have, but how you choose to perceive it. Close your eyes for a moment. Picture a sky completely empty. Not dark, not star-filled, but blank. No pinpricks of light, no warmth, no shimmer, just a vast silence waiting to become something. But something was coming. In the vast void, tiny fluctuations in density, leftovers from quantum ripples frozen during inflation, began to tug matter into clumps, hydrogen, helium, a sprinkle of lithium. These clouds began to gather, collapse, heat, and finally ignite. The universe's first stars were born, and they were nothing like the stars we know today. We call them population 3 stars. Though none have ever been seen directly, they were made entirely of primordial elements. No carbon, no iron, no heavy metals, and because of that, they were monsters, massive, short-lived, and incredibly hot. Some may have been hundreds of times the mass of our sun. They burned bright blue-white, roaring through their fuel in just a few million years, a blink on the cosmic clock, before dying spectacularly in supernovae or collapsing directly into black holes. But these stars were more than just violent lights. They were alchemists. In their fiery cores, they forged the first elements heavier than helium, carbon, oxygen, nitrogen, the ingredients for planets, for oceans, for life. When they died, they scattered these elements into the universe, enriching their surroundings. The next generation of stars, population 2, formed in these enriched clouds, and finally the building blocks of galaxies, solar systems, and organic chemistry began to emerge. Everything you are, every breath, every cell, every atom in your body was once part of this ancient star stuff. And though we've never observed a population 3 star directly, we've seen their echoes. In the chemical signatures of the oldest stars still shining, in the ratios of elements in distant gas clouds, in the background hum of light that fills the universe, the cosmic infrared background, believed to hold faint traces of these ancient giants. Even now, telescopes like the James Webb Space Telescope are scanning the distant edges of the cosmos, hoping to catch the light of the first stars, not by seeing the stars themselves, but by witnessing the galaxies they helped form. You, lying there in the dark, are part of a legacy written in starlight. Some photons released by those first stars are only now reaching Earth, slipping through our atmosphere, bouncing off your eye, your retina, your mind. You, a creature of bone and breath and boredom, are intercepting messages sent more than 13 billion years ago. How strange. How wonderful. But the story doesn't end there. The first stars didn't just make elements. They made black holes, big ones. And there's growing evidence that these early black holes, seeds planted in the cores of young galaxies, may have grown into the supermassive black holes we see today. Yes, even the one at the center of our Milky Way. And all of it started with a star that no longer exists. Even more mysterious are the strange stars, theoretical remnants of that early era. Some astrophysicists speculate that quark stars or dark stars may have formed in those early days, fusing exotic matter or powered not by fusion, but by dark matter annihilation. We haven't found them yet, but the math says it's possible. And if we ever do find one, even one, it would mean the early universe was even stranger than we ever dreamed. This is what echoes mean. They're not sounds, they're not light, even. They are patterns, ripples, fingerprints left behind in the structure of reality. They are fossils of flame. The first stars may be gone, their light extinguished, their cores collapsed, but their influence is eternal. Every later star carries their chemical legacy. Every planet reflects their contributions. Every tree, every ocean, every strand of DNA sings with the atoms they forged in their death throes. In that sense, they are not gone at all. They are you. So next time you stare at the sky and feel small, remember this. The sky is your ancestor. The stars are your inheritance. And every quiet breath you take is an echo of fire that burned before the Earth had even formed. Welcome to Saturn, the jewel of our solar system, not just for its beauty, but for its unsettling complexity, a planet of swirling storms, icy moons, and the most iconic ring system ever witnessed. But the deeper you go, into those rings, under their shadows, into Saturn's swirling depths, the stranger things become. And the more the universe starts to whisper, you don't really understand me at all. Let's begin with the rings. To the casual observer, Saturn's rings look like solid bands, elegant and thin, but up close, they're a storm of debris, billions of particles from dust-sized grains to house-sized chunks of ice and rock, each orbiting independently. They're moving at incredible speeds, forming a constantly shifting ballet of collisions, spirals, wakes, and resonance patterns. Nothing about them is still. In fact, the rings are so dynamic that they literally sing. Using radio instruments aboard spacecraft like Cassini, scientists have converted the electromagnetic vibrations of the ring system into audible tones. The result? An eerie echoing hum, something between wind chimes and alien whale song, produced by gravitational interactions between the rings and Saturn's moons. Some parts of the rings ripple like a pond touched by invisible fingers. Others carry spiral patterns caused by gravitational nudges from Saturn's many moons. These patterns rotate and propagate over time, recording collisions and near misses like grooves on a vinyl record. And then there's Enceladus, a moon not far from the E-ring. This frozen world, only about 500 kilometers across, was once assumed to be just another dead rock. But then Cassini flew past it, again and again, and what it found beneath the icy surface shocked the entire field of planetary science. Let that sink in. Beneath the ice of a tiny moon, in the shadow of Saturn's rings, a liquid ocean, dark, pressurized, full of organics, possibly hosting the right conditions for life. You're lying in bed, wrapped in gravity and silence, while water, maybe full of microbes, drifts through space, falling like invisible snow into the void. It's beautiful and disturbing, but it doesn't stop there. Inside Saturn itself, the layers become even more chaotic. The surface, if you can even call it that, isn't solid. The upper atmosphere is composed of bands of ammonia clouds, massive storms and wind speeds that can exceed 1,800 kilometers per hour. That's faster than any hurricane on Earth. The storms near Saturn's equator and poles rage without pause, driven by processes still not fully understood. Then there's the hexagon, a persistent six-sided jet stream that circles Saturn's north pole, wider than two Earths laid side by side. How does a storm become a shape? No one knows for certain. Some suggest standing waves in Saturn's atmosphere, or complex interactions between wind layers, but there's something inherently unsettling about a storm so large, so old, and so mathematically precise. It's like the planet is keeping a secret, a geometric whisper in a world made of gas. And deeper still, Saturn may not have a solid surface as we know it, but it does have a core, or something like one. Based on gravitational data, scientists now believe Saturn's interior is fuzzy, with a diffuse semi-liquid core that blurs the line between rock and gas. The boundary isn't crisp, it's gradual, murky, shifting with pressure and time. Even gravity behaves strangely here. Cassini's final orbits, known as the grand finale, were designed to slingshot between the planet and its innermost ring. The data it returned was startling. The rings are far younger than the planet, perhaps only 100 million years old, a blink in cosmic time. That means they might be temporary. They could vanish, torn apart by Saturn's gravity, dragged down by magnetic fields, or consumed by the planet's atmosphere in a slow, glittering rain. And someday, the night sky might lose its most famous adornment. Saturn, the ringed wonder, will look like just another gas giant. The chaos beneath its rings will quiet, the icy debris will fall, grain by grain, and all that will remain is memory, in telescopes, textbooks, and the lingering questions about what we once saw there. This is what makes Saturn terrifying in the gentlest way, not because it's violent, though it is, not because it's big, though it dwarfs you in every way. What we see now, those rings, those storms, that perfect hexagon may one day vanish, and will be left with only data, and a few fading images of a world that danced briefly and beautifully through our understanding. A planet that held oceans beneath ice, storms shaped like geometry, and rings that hummed with gravity's music. A place both real and ephemeral. Let's talk about the sun. You know it as the constant in your life, the familiar, glowing disk that rises and falls each day, warming your skin, illuminating your morning coffee, and telling your body when it's time to rest. The sun feels reliable, predictable, comforting, like the ticking of a clock or the gentle breath of the planet itself. But when you zoom out, when you stop thinking of the sun as ours, it becomes something much stranger, much more alive, and much more dangerous. Let's begin with what the sun actually is. Not a solid object, but a roiling sphere of plasma, a fusion furnace, so enormous it holds 99.8% of all the mass in the solar system. Think about that. If you gathered up all the planets, moons, asteroids, and comets, mashed them into one colossal object, the sun would still outweigh them 500 times over. The sun's surface, or what we call the photosphere, is not smooth, it's textured, boiling with convection cells the size of continents. Beneath that surface, nuclear reactions rage in the core, where hydrogen atoms are crushed together to form helium, releasing energy in the process. This energy takes thousands of years to crawl outward through the dense inner layers before finally escaping as light. And that sets the gentle version of the story. Because above the photosphere lies the corona, an outer atmosphere that makes no logical sense. It's hotter than the layers beneath it. A lot hotter. While the surface of the sun sits at around 5,500 degrees Celsius, about 10,000 degrees Fahrenheit, the corona can spike to millions of degrees. This violates classical thermodynamics. Imagine touching a stove and then finding that the air above it is hotter than the stove itself. Scientists believe magnetic fields might be the culprit, violently twisting and snapping, releasing waves of energy into the upper atmosphere. But the truth? We still don't fully understand how or why it happens. The sun keeps that secret. Sometimes the sun erupts. But more violent still are coronal mass ejections, CMEs. These are not just bursts of light. They are entire waves of plasma and magnetic field, hurled through space like solar tsunamis. A large CME can take days to reach us, but when it does, it can cause geomagnetic storms. Power grids can fail. Communication systems can collapse. Entire continents can experience cascading blackouts, not from war or sabotage, but from a star having a bad day. SEPs happened before. In 1859, a massive CME struck Earth in what became known as the Carrington Event. Telegraph wires caught fire. Aurora Borealis was visible near the equator. If such a storm happened today, our technology could be devastated, not permanently but deeply, suddenly and expensively. And the sun would keep spinning, unbothered, alive. Because that's the other thing. The sun is not static. It breathes in cycles. Approximately every 11 years, its magnetic field flips. North becomes south. Sunspot activity waxes and wanes. Periods of relative calm give way to periods of chaos. Right now, we're ramping into another solar maximum, and scientists are watching closely. Now, zoom in. The sunspots. They're not just blemishes, they're cooler, darker regions where intense magnetic fields twist and tangle. They're often the source of solar flares and CMEs. And from Earth they look like bruises, like the sun is showing its stress. The sun has moods. It's been through grand minima, long periods where sunspot activity nearly vanished. During the Maunder Minimum in the 17th century, Europe experienced unusually cold winters, failed crops, and chilling silence from the sun's usual roar. We don't know why it happened. We don't know when it will happen again. And then there's this question: what happens when it dies? Because the sun will die. Not today, not tomorrow, but in about 5 billion years, the hydrogen in its core will run low. The sun will swell into a red giant, consuming Mercury, Venus, and maybe even Earth. It will burn brighter, but crueler. The oceans will boil. The sky will darken with escaping atmosphere. Earth will no longer be a home, just a scorched rock circling a swollen flame. Eventually, the sun will shed its outer layers, leaving behind a white dwarf, a hot, dense core about the size of Earth, but with half the sun's mass. It will sit quietly for trillions of years, cooling slowly, fading into a black dwarf, a theoretical object we've never seen because the universe isn't old enough for one to exist yet. But don't set panic. In your lifetime, and for millions of generations, the sun will remain, warming our backs, feeding our plants, pushing shadows across the floor at noon. It will keep its secrets, hum its radiation, and spin its magnetic stories into space. Just remember, it is not a ball of light. It is a living star, unpredictable and unknowable, and the only reason you exist is because it's been relatively calm for a few billion years. So tonight, as you drift towards sleep, picture it. That glowing orb, not rising or setting, but seething. A furnace in the sky, a god we stopped worshipping only because we gave it a name. And it still burns. Let's say you walk outside one night, look up and spot a twinkling star. It's faint. Maybe it's blue, maybe orange. You pause for a second. It's pretty, sure, but unremarkable. Just another point of light in a sky full of them. But here steps the trick. That star might be dead. Gone. Vaporized. Exploded into the void before you were ever born. Maybe before the pyramids were built or before humans even existed. And you're just now seeing the light it left behind. Welcome to the uncanny time travel trick of space. The deeper you look into the cosmos, the further back in time you're seeing. And sometimes, the source is long gone. Now imagine a star, 10 times the mass of our sun. It burns fast, bright and reckless. Unlike the sun, which paces itself like a slow cooker, This massive star is like a blowtorch on full blast. It uses up its hydrogen rapidly, burning through helium, carbon, oxygen, silicon, each new layer piling up in the core like an unstable stack of elements. And then it hits iron. Iron is the dead end. You can't fuse iron and get energy out. And so the core collapses. Gravity pulls everything inward at horrifying speed, and in a fraction of a second the star explodes, a supernova. What does that mean? Well, for one, it gets bright. Really bright. So bright, in fact, that a supernova can outshine an entire galaxy for a few days. In 1054 CE, Chinese astronomers recorded a guest star in the sky that stayed visible even during the day. What they saw was the Crab supernova, and its remnants are still expanding outward to this day, a swirling cloud of debris in the Taurus constellation. That's not a myth. It happened, and the echo of that death still ripples through the galaxy. Supernovae aren't just dramatic, they're also essential, because the elements that make up your body, iron in your blood, calcium in your teeth, gold in your jewelry, were forged in the death throes of stars. You are literally made of exploded stardust. You were born from death, and that death happened billions of years ago, long before anyone could call it beautiful. Some stars die even more violently. If a supernova's core is massive enough, it doesn't stop collapsing. It becomes a neutron star, an object so dense a teaspoon would weigh 1 billion tons. And sometimes the core collapses further still, becoming a black hole, tearing a hole in space-time itself. These aren't science fiction. They're out there, right now, silent, invisible, drifting through the galaxy, and the stars that made them. Long gone, their last scream of light passed Earth millennia ago. But you still see them. The light lives on. When you look at the night sky, you are not seeing the present. You are seeing a patchwork of ancient light, each dot a kind of celestial obituary. Some of those stars are still alive, others are not, but you'll never know which is which. Not yet. The closest recent supernova visible from Earth was SN 1987A, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It appeared in 1987, a quiet flash in the sky that telescopes quickly turned toward. But the star that created it, that one died 168,000 years ago. We only caught up to its light in the 20th century. It's like watching a movie on delay, except the projector is 100,000 light years away, and the theatre burned down before the dinosaurs. And now here sits the eerie part. There could be a supernova in progress right now, somewhere in the sky, and you wouldn't know. Not yet. Not until the light gets here. Astronomers suspect Betelgeuse, the reddish shoulder of Orion, may be nearing the end of its life. It's large enough. It's unstable enough. And if it explodes, it will be visible from Earth, maybe even during the day. But it may have already exploded. We just haven't seen the light yet. So the next time you go stargazing, think about that. Each twinkle might be the last breath of a long-dead sun. Each constellation might be telling a story that ended long ago, and yet those stories still reach you. They cross impossible distances. They outlive wars, species, even planets. Because light is memory, and the universe is full of memories, drifting toward us in silence. So yes, some stars exploded before you were born. Some are exploding now, and some will explode long after you're gone. But they're light. That keeps traveling. There's a planet out there that breaks all the rules. Astronomers sometimes call it a hot Jupiter, but even that doesn't do it justice. Imagine a gas giant the size of Jupiter, maybe even bigger, sitting right next to its star. Not far away like our Jupiter, not nestled safely in the cold outskirts of its system. No, this one is so close to its sun that a single year lasts just a few days. It's scorched. It's bloated. It's impossibly close to destruction. By all the rules of planetary formation, this planet shouldn't exist. And yet, it does. Let's unpack why this is so strange. In our solar system, everything feels tidy. The small rocky planets like Earth and Mars orbit close to the Sun. The gas giants, Jupiter, Saturn, Uranus, Neptune, fall much farther out, where it's cold enough for gases to condense and clump together. That's planetary formation 101. The further out you go, the more raw material is available to make giants. And the closer in you go, the more difficult it becomes for gas giants to even form, let alone survive. So when we started discovering hot Jupiters in other solar systems, it threw everything into chaos. The first one we found was 51 Pegasi b in 1995. It orbits its star in just 4.2 days. That means it's screaming around its sun at incredible speeds, bombarded by solar radiation and heated to over 1,000 degrees Celsius. No planet that size should form that close. And if it did somehow wander inward, tidal forces from the star should eventually tear it apart. But it sits still there, holding on. Scientists think it may have migrated. Maybe it formed far out, like our Jupiter, and then drifted inward, pulled by gravitational tugs or a chaotic collision with another planet. But that raises even more questions. How did it survive that journey? Why didn't it get slingshotted out of the system or fall into the star? Why didn't its orbit destabilize everything else? We don't know. You still don't understand how I work. Even stranger, there are planets and galaxies beyond our own. We've spotted candidates that orbit stars 30,000 light-years away. Based on faint dips in light or gravitational microlensing, the brief, lens-like effect a planet has when it passes in front of a distant star. These aren't science fiction. These are detections we've made with real telescopes, backed by real data. And sometimes, the planets we find seem to laugh at our models. Some are rogue planets, wandering through the galaxy without a star at all, just drifting. Cold, lost, born in the system perhaps, but ejected, exiled by gravitational chaos. Imagine a world where the sky never brightens, where there is no orbit, no sunrise, no anchor. These aren't set rare mistakes. They set reminders. The universe doesn't care about our neat categories. And here sits where it gets existential. Some are puffy, like cotton candy. Some are denser than lead. Some orbit 2 stars. Some orbit none. Some rain glass. Some have metal clouds. Some may be tidally locked, showing one face to their sun forever, a side of eternal fire and a side of endless frost. And every time we point our telescopes outward, we find more anomalies. Which brings us back to the planet that shouldn't exist. Maybe it's not one planet. Maybe it's a category, a growing list of outliers that teach us to doubt our expectations. Maybe the universe isn't built on consistency. Maybe it thrives on chaos. Or maybe, and this is the strangest theory of all, we're seeing only the survivors. Think of it like this. Maybe there were billions of weird planets, but only the rare ones stabilized. Only the lucky ones avoided destruction, and only those are visible to us now. The rest, gone. So when we look at 51 Pegasi b or other planets that make no sense, maybe we sit here not seeing a rule breaker. Maybe we sit here seeing a miracle of cosmic balance, an improbable survivor, a message in gravity saying, yes, I made it. Against the odds, I'm still here. There are planets that shouldn't exist, but they do. And maybe, just maybe, so do you. You already know about Saturn. Its rings are iconic, vast, shimmering bands of icy debris that wrap around the gas giant like a divine crown. They've been visible through telescopes since the 1600s, and for centuries they seemed like an elegant exception. Beautiful, majestic, a curiosity of one planet. But then came Voyager, and Cassini, and Hubble, and suddenly we realized something unsettling. Saturn isn't set alone. Jupiter has rings. Uranus has rings. Neptune has rings. Even tiny icy dwarf planets like Chariklo, just 250 kilometers wide, have rings. And then we found Halmia, spinning fast in the outer solar system with a ring of its own. The evidence kept piling up. Rings are everywhere, and many of them shouldn't exist. Let's rewind. Rings are thought to form from debris. When moons collide, or comets shatter, or asteroids wander too close and get torn apart by gravity, their pieces don't always disappear. If they fall within a planet's Roche limit, the region where tidal forces prevent them from reassembling, they remain trapped, spread out, flattened, spinning, and voila, a ring. But here sits the twist. Rings are supposed to be temporary. They don't last forever. They decay, they scatter, they fall into the planet, or get pushed out by solar radiation or plasma from magnetic fields. Most simulations suggest planetary rings should fade in a few million years. Yet Saturn's rings are still bright, still sharp, still massive. They don't look ancient, they look young. According to recent data from the Cassini spacecraft, which orbited Saturn for over 13 years, the rings are likely less than 100 million years old. That's a blink in cosmic time. Earth already had dinosaurs. The solar system was well formed, so where did these fresh, vibrant rings come from? One theory: a moon died. A large moon, maybe as big as Mimas or Iapetus, ventured too close, broke apart, and left behind its icy remains. That might explain the ring system's mass and composition, but it raises other questions. Why only Saturn? Why not other giants? Why now? And then we found Chariklo. This is where things get weird. Chariklo isn't a planet, it's a centaur, a small object that orbits between Saturn and Uranus. It's too small to pull itself into a sphere, and yet it has 2 rings. How? Why? What kind of cataclysm created that pattern around something so tiny? It shouldn't be possible. There's no strong gravity, no thick atmosphere, no shepherd moons to stabilize the structure. Yet the rings are there, narrow, neat, perfect, balanced, suspended. And now we've found rings around an exoplanet, a planet in another solar system. In 2015, astronomers observed a star named J 1407 dimming in a strange, stuttering pattern. It didn't look like a planet passing in front of it. It looked like a planet with dozens of rings, far larger than Saturn's, a ring system 200 times bigger. We call it Super Saturn. But the light doesn't lie. Now consider this. We're not just finding rings where we shouldn't. We're finding stability where chaos should rule. Rings require a delicate balance, gravitational forces, orbital resonances, particle sizes, shepherd moons, and more. The slightest nudge should collapse them. And yet, these impossible structures persist, like ancient tapestries fluttering in space. Some physicists think rings are more ephemeral than we imagined. They form and vanish regularly in cosmic time, and we just happen to be alive during a ring-rich era. Others suggest they're resonant phenomena, held in place by a kind of invisible choreography, moons pulling at just the right speeds to sculpt the debris. Still others wonder if we're missing something fundamental about how matter organizes in space. Perhaps rings aren't rare accidents. Perhaps they're natural attractors, gravitational quiet zones where dust and ice linger by default. Then again, maybe it's just cosmic coincidence. Maybe Chariklo's rings won't last another 10,000 years. Maybe Saturn's are already starting to fall. Maybe we're living in the final moments of their brilliance, lucky observers catching the end of a celestial event that won't repeat. Rings aren't just aesthetic. They tell us about collisions, about violence, about death. Every ring system is a graveyard, a collection of shattered bodies, lost moons, failed worlds. They are the cosmic equivalent of ruins, orbiting in silence, and yet they shimmer, they beautify, they endure. There sets poetry in that. Because sometimes the most beautiful structures in the universe are born not from design but from destruction, from the remnants of what once was, from things that broke and kept moving. So the next time you see a picture of Saturn, don't just admire the rings. Think about what they mean, about how they got there, about why they set still here when they shouldn't set be, and about how, just maybe, even in space, nothing is ever truly gone. You look up at the moon and think of silence. Cold, cratered rock, stillness. You imagine that's how all moons must be. Dead, inert, echoing their planet's gravity without doing much of anything else. But that's not the case. Not even close. Across our solar system, there are moons that shouldn't just be orbiting. They shouldn't be, by all known logic, alive. But they are. Let's start with Io, a moon of Jupiter. It's slightly larger than Earth's moon, but that's where the similarities end, because Io is the most volcanically active body in the entire solar system. Not Earth, not Venus. Io. Its surface is constantly reshaped by massive eruptions, lava fountains that rise dozens of kilometers high, reshuffling the crust like a slow-motion nightmare. There are no impact craters because they don't last long. The surface is erased and rewritten like a living skin, a moon with a heartbeat. Io doesn't have tectonic plates like Earth. It doesn't orbit particularly close to the Sun. It should have cooled off eons ago, and yet beneath its crust it boils. The answer lies in a violent tug-of-war. Io is locked in a gravitational resonance with its siblings, Europa and Ganymede, and together they pull and stretch it constantly as it orbits Jupiter. This endless flexing creates tidal heating, a kind of internal friction that melts rock and fuels its eruptions. So we've got a volcanic moon. Fine, maybe that's just Jupiter being dramatic. But then there sits Enceladus, orbiting Saturn. This icy moon, only 500 kilometers wide, should be frozen solid, too small to hold heat, too far from the sun to matter. But Cassini, our spacecraft that spent over a decade exploring Saturn, found something astonishing: jets of water. Enceladus has a global ocean beneath its crust, and it's leaking. That's not just curious, that's potentially habitable. Now hold on to that thought, because just a bit farther out, orbiting Jupiter again, is Europa, slightly smaller than our moon, covered in cracked ice and long scars, as if the surface had been shattered and refrozen again and again. And beneath that fractured surface, a saltwater ocean, estimated to be twice the volume of all of Earth's oceans combined. Europa has tides, driven by Jupiter's gravity. Its icy crust moves, flexes, hums, plumes of water shoot into space, like Enceladus, and once again we find the recipe: water, heat, organics, and energy. But Europa isn't set alone. Look at Titan, Saturn's biggest moon, bigger than Mercury. Even, it's the only moon with a thick atmosphere, denser than Earth's. You could walk on it without a spacesuit, just a breathing mask and a heavy coat, because it's cold. Very cold. But strange things happen on Titan. There are rivers, lakes, and rain, not of water but of liquid methane and ethane, a hydrocarbon cycle eerily similar to Earth's water cycle, plays out on a frozen world over 1 billion kilometers from the sun. There are dunes, weather, even possible cryovolcanoes that spew water instead of lava. And deep underground? Again, a subsurface ocean of liquid water, possibly salty, possibly active. One by one, the moons keep defying our expectations. They aren't quiet, forgotten leftovers of planet formation. They're dynamic. They have atmospheres, weather systems, volcanoes, oceans, and maybe, just maybe, the conditions for life. So what does that mean for us? It means we may be looking in the wrong places. For years we searched Mars for signs of water, and we found some, a little here, a little there. But Mars is dry and exposed. Its atmosphere was stripped away. Its surface is bombarded with radiation. Even if there was life once, it would be a ghost by now. But beneath the crust of Europa or Enceladus, life could be thriving, hidden from view, safe in the darkness. Some scientists now believe that moons, not planets, might be the best bet for finding alien life, because these icy satellites have something crucial: internal heating. It doesn't matter how far they are from the sun, they make their own energy through gravity, friction, and resonance. They aren't waiting for warmth, they generate it. And that flips everything. And they set not just theoretical, they're right here, in our own backyard. Enceladus, Europa, Titan, Ganymede, Callisto, Triton. Pluto's moon Charon might even have a layered ocean. The more we look, the more we find. Moons that shouldn't sit to be warm. Moons that shouldn't have oceans. Moons that shouldn't, by any logic, be alive. But they are. They breathe. They shift. They shimmer. And someday we might send submarines beneath their crusts. Not to conquer, not to mine, but to listen, to drift, to find out if something else is already listening back. Imagine for a moment drifting away from every star you've ever known. You are leaving behind the Milky Way, its spiraled arms full of heat, hydrogen, dust, and memory. You pass the edge of the halo, where dim globular clusters hover like forgotten beads on an old celestial necklace. And then there's nothing. No stars, no suns, just a silence so complete that it doesn't feel like silence. It feels like the absence of the idea of sound. These are not simply dark places. They are unimaginably vast regions of space where galaxies are separated by millions of light years. Most of the universe is made of this. Emptiness, silence, isolation, cosmic deserts that stretch beyond comprehension. If you stood, or rather floated, in one of these voids, the nearest galaxy might be so faint it would appear as a soft smudge on your peripheral vision. Light, though moving at 300,000 kilometers per second, would take millions of years to reach you from any meaningful object. And in every direction there is only the slight curve of distant light, the skeletal remains of galactic limbs peeking over cosmic hills. These voids aren't the kind of emptiness you find in a vacuum chamber. Even in the best vacuums on Earth, you're still dealing with trillions of molecules per cubic meter. But in the cosmic voids, you might find one hydrogen atom every several meters. One atom, just floating, waiting, as if it too doesn't know why it's still there. And yet, even in this cosmic desolation, there are secrets. Take the Boötes void, for instance. Discovered in 1981, it's one of the largest known voids in the observable universe. It spans over 330 million light-years across. To give you a sense of scale, if the Milky Way were a grain of sand, this void would be the size of Mount Everest. And within that emptiness, only a handful of galaxies, maybe 60 or so. It should contain thousands. It doesn't. No one really knows why. Some cosmologists propose that these voids are just the natural result of the large-scale structure of the universe. After the Big Bang, matter clumped under gravity, forming filaments and walls, like veins in marble, and left behind hollow spaces in between. Think of soap bubbles packed together. The bubbles are the galaxies, and the space between them, that's the void. Only these voids are older than any stone, and larger than any thought. Other scientists wonder whether dark energy, that mysterious force accelerating the universe's expansion, might have a more complicated relationship with these voids than we understand. Could these emptinesses be stretching? Could their growth be accelerating faster than the rest of the universe? And then there's the question no one wants to ask out loud. Why is the universe built this way at all? One idea suggests that the voids are necessary. Without these empty stretches, gravity couldn't pull the matter together into galaxies. Stars wouldn't form, Planets wouldn't condense. Life wouldn't blink into existence. The void is not a mistake. It's the necessary silence that allows the cosmic music to form at all. But it gets stranger. Recent studies have shown that these voids aren't entirely passive. Some data suggests that they might have a subtle repelling effect, that galaxies on the edges of these voids are being pushed outward ever so slightly. If true, it implies that the void is more than an absence. It's a participant in the structure of space itself. Imagine walking through a haunted house, only to realize the shadows on the wall are moving not because of your flashlight, but because the shadows themselves are alive. The universe is like that. Even the darkness may be doing something. If this all feels too large, too abstract, return to your breath. Because even as you lie in your bed, drifting towards sleep, your own body is filled with empty space. The atoms that make up your skin, your bones, your lungs, they are mostly void. The electrons spin in clouds far from the nuclei. You are, in every measurable way, mostly empty. And yet, you are here, you think, you feel. Perhaps the void isn't a mistake. Perhaps it is the medium in which meaning is born. So float, if only in your mind, between the galaxies. Let your thoughts grow thin, like starlight stretched across time. Let the silence hold you. Let the emptiness remind you that even in the greatest absence there is structure, there is story, there is something waiting to be noticed. The void is not lonely. It is vast. Yes, it is quiet, but perhaps it is just resting. And now, as we drift onward through the next corridor of the universe, you might find yourself wondering what else is hiding in the dark. We could look, but only gently. Hello again, floating traveler. By now, you've drifted through star nurseries, passed through intergalactic voids, watched galaxies spin like frozen fireworks, and learned to see darkness not as emptiness, but as structure. But here, in this new space, we approach a deeper mystery. Welcome to the region of the universe, influenced by something we call the Great Attractor. Let's begin simply. You may know that our home galaxy, the Milky Way, is not standing still. It's hurtling through space at approximately 600 kilometers per second. That's over 2 million kilometers per hour in a specific direction. This motion is not random. Something massive is tugging at our galaxy, tugging at all the galaxies in our local group, and many beyond that, a great flow of galaxies all streaming toward a region of the sky. It's called the Zone of Avoidance, a patch of sky obscured by the thick plane of our own Milky Way, where gas, dust, and stars block our telescopes from seeing clearly. Behind that veil lies the Great Attractor, a region exerting gravitational influence over hundreds of thousands of galaxies across hundreds of millions of light years. Now take a breath. You are being pulled by something you cannot see. Something so massive, so distant, so cloaked, that it warps the entire structure of the observable universe around it. So what do we think it is? Some theorists suggest that the Great Attractor isn't a single object at all, but a dense region of clusters, superclusters, and dark matter. Galaxies, galaxy clusters, and dark filaments of cosmic web, all crammed together in one gravitationally powerful direction. Others propose that it might be part of an even larger structure, the Shapley supercluster, an even more massive congregation of galaxies over 650 million light-years away. If that's true, then the Great Attractor is merely the nearest ripple in an even deeper current. And there's steps more. In 2014, scientists confirmed a vast cosmic flow called the Laniakea supercluster, a mind-stretching structure of over 100,000 galaxies, including our own. The name means immense heaven in Hawaiian, and the Great Attractor lies near the center of it. Imagine the universe as a basin, with all galaxies sliding inward toward one gentle slope. That slope would be shaped by the gravity of this invisible force. But let's pause. There's something poetic, maybe even a little spiritual, about being pulled by something you can't see. It mirrors so much of human experience, doesn't it? We are moved by longing, by memory, by forces hidden in the unconscious. We follow desires we don't understand. We orbit questions we can't answer. The Great Attractor is not just an astrophysical puzzle. It is a metaphor, a reminder that even in a universe governed by light and gravity, mystery holds the center. Still, the science demands more. Some astronomers believe that dark matter is responsible, an unseen glue holding the structure of the universe together. Others point to dark energy, the force pushing galaxies apart, and wonder if we're witnessing a strange balance between the pull of gravity and the stretch of expansion. The truth? We don't yet know. We see the fingerprints, the ripples, the implications, but not the thing itself. And perhaps we never will. As our instruments improve, we may map more of the zone of avoidance. We may one day know what lies behind the curtain. But for now, the Great Attractor remains exactly what it sounds like. Great and attracting and just beyond our reach. So as you lie there, listening, drifting further into the quiet of space and thought, remember that you are not stationary. You are moving. You are being pulled, not just by gravity, not just by history or a habit, but by something mysterious and unseen. Some part of the universe has its hand on your shoulder, guiding you forward, gently, silently, toward the next mystery, toward whatever comes next. And that is where we are going to. Hello again, drifting consciousness. You've heard of them, these collapsed stars that suck in all light, these cosmic vacuums that devour everything, gas, dust, planets, even time itself. But what if some of them shouldn't exist? Not just because they're terrifying, but because their very presence seems to break the rules. Let's begin quietly, with something that seems impossible. Astronomers have found black holes that are too big, too early. That is, we've observed black holes in the early universe, just a few 100 million years after the Big Bang, that have already grown to be billions of times the mass of our Sun. Take quasar J 03131806 for example, a supermassive black hole existing just 670 million years after the Big Bang. It weighs in at 1.6 billion solar masses. That's like finding a fully grown adult just days after birth. And here's the problem: based on everything we think we know about star formation, accretion, and gravitational collapse, these black holes shouldn't have had enough time to grow that big, not unless the universe gave them a massive head start, or unless we're missing something important. Let's break it down. Black holes usually form when massive stars collapse under their own gravity at the end of their lives. These are called stellar mass black holes, and they're typically a few times the mass of our Sun. Now, if these black holes sit in a dense environment, like the center of a galaxy, they can slowly feed on gas, dust, and stars around them. Over millions or billions of years, they grow into supermassive black holes, millions or billions of solar masses. But here's the catch: that process takes time. Lots of it. There's a natural limit to how fast a black hole can feed, called the Eddington limit. If it eats too fast, radiation pressure pushes matter away, like steam blowing off a kettle, so the black hole can only gorge itself so quickly. And yet, we find these monsters early. Black holes that are far too large for their age. Black holes that, by our equations, shouldn't be possible. So how did they get so big, so fast? One theory proposes direct collapse black holes, the idea that under certain conditions in the early universe, entire gas clouds could have collapsed directly into black holes without forming stars first. This shortcut would allow for much larger seeds, bypassing the need for a slow and steady diet. Others suggest primordial black holes, formed not from stars at all, but from dense regions in the early universe itself, moments after the Big Bang. These black holes would have been born big from the raw fluctuations of space-time during cosmic inflation. Then there's the possibility that our understanding of black hole physics, or even of time, is flawed. What if space evolved differently than we thought? What if time flowed differently in those early epochs? What if black holes are tapping into something more exotic like dark matter that fuels their rapid growth in ways we haven't yet seen? And what if the black holes we observe are only the surface of something deeper? Some physicists wonder if black holes are gateways, not just collapsed stars, but connections to other regions of space-time, wormholes perhaps, or tunnels through a multiverse. Theories like loop quantum gravity or string theory flirt with this idea that a black hole is not the end of something but a fold in the cosmic sheet. The James Webb Space Telescope, launched into the quiet, has begun to peer further than ever before, and what it sees continues to surprise us. More early galaxies, more young quasars, more enormous black holes shining across time, and always the quiet question, why are they there? Let's sit pause. You are floating in the darkness, far from Earth, far from light. You pass a quasar, a brilliant beacon of radiation powered by a supermassive black hole at its core. You feel nothing. You see only the glow, but at the center of that brilliance is a void, a singularity where time itself ends. Now multiply that by billions. The universe is filled with these monsters, not just sitting quietly, but actively shaping galaxies, bending light, steering the evolution of stars. Some black holes lie dormant, like sleeping giants. Others roar, feeding voraciously, launching jets of plasma thousands of light years into space. And yet, despite their destructive potential, we now think black holes might be essential. Galaxies form around them. Matter organizes around their gravity. Even life, in its long and tangled journey, may depend on the existence of these impossibilities. They are death, yes, but also structure, also origin, also a necessary silence at the heart of the story. So when you hear the phrase black holes that shouldn't exist, maybe it's not just about mass or time, maybe it's about the contradiction they represent. They are absence that creates form, rules that seem to break themselves. And as you drift further into sleep, just know you too are part of this paradox. Living matter made of stardust, consciousness floating in a universe that was never supposed to be so alive, so strange, so beautifully self-aware. You are real, and yet, the more we discover, the less we understand. Not answers, but wonder. Picture the universe not as chaos, but as choreography, a slow, spiraling waltz of galaxies, atoms and light, a pattern that repeats, a balance that holds, a symmetry that against all odds refuses to break. You've likely heard it before, that the universe tends toward disorder, entropy, the great decay, yet within this descent into chaos, something peculiar clings to order. Particles come in pairs, forces mirror one another, equations balance, even the laws that govern existence seem symmetric. But is this just how we see things? Or is there something deeper, a hidden structure guiding the way everything unfolds? Let's begin with the most basic of observations, matter and antimatter, two sides of the same coin. Every electron has a mirror twin, the positron. Every proton has an antiproton. In theory, at the beginning of time, matter and antimatter should have been produced in equal amounts, perfect symmetry. And yet, look around. Where is all the antimatter? We're here, made of matter. Stars are made of matter. Planets, moons, you, this voice, all matter. Antimatter exists, yes, but it's rare, hunted down in particle accelerators or fleeting in cosmic rays. If the universe began in symmetrical birth, why is it so unbalanced now? This is known as the baryon asymmetry problem, a quiet scandal in cosmology, a mystery without a satisfying ending. Some theories propose that shortly after the Big Bang, certain processes, subtle, tiny, violated symmetry, just enough to give matter the upper hand. These violations are called CP violations, standing for charge parity. They're difficult to observe, and even harder to explain, but they leave us with the most obvious of evidence: existence itself. But this isn't the only symmetry under question. Let's consider mirror symmetry, the idea that physics should behave the same if flipped. Imagine watching the universe in a mirror. Left becomes right, spins reverse. Shouldn't the physics remain identical? In many cases, it does. But not all. Certain interactions, particularly involving the weak nuclear force, break mirror symmetry blatantly. In 1956, physicists Qian-Xing Wu and her colleagues performed an experiment that shocked the scientific world. They demonstrated that parity is not conserved in weak interactions. The mirror lied. Nature had a preference, a handedness. Imagine if suddenly your reflection refused to mimic you. Lift your right hand, and it lifts its right hand, not the left. It's no longer you in the glass. It's something else. This is the unsettling realization physicists faced. The universe, while elegant, is not perfectly fair. It has preferences, asymmetries. Yet, despite these violations, symmetry still dominates. Take Noether's theorem, a quiet masterpiece of mathematical philosophy. Emmy Noether, one of the most brilliant minds you may never have heard of, showed us that for every symmetry in physics, there is a corresponding conservation law. If a system behaves the same regardless of time, then energy is conserved. If it behaves the same regardless of position, momentum is conserved. If it behaves the same regardless of direction, angular momentum is conserved. In other words, the very order of the universe, the fact that things behave consistently, is rooted in symmetry. Strip away the poetry, and you still find law. Strip away the law, and you may find nothing. Zoom out. Galaxies form in great filaments across the cosmos, vast structures spanning hundreds of millions of light years. These web-like forms show a kind of fractal symmetry, similar patterns repeating across different scales. Zoom in. Crystals, snowflakes, even DNA, all share symmetric structures. Why? Is it because symmetry is beautiful, efficient, or is it because the rules of the universe demand it? In quantum mechanics, symmetries are even more sacred. They determine which particles can exist, which forces are allowed, the Standard Model. Our best attempt to catalogue the zoo of subatomic particles is built almost entirely from symmetry groups. Complex, abstract mathematics, but all rooted in the same basic principle: structure. But not all physicists are convinced this symmetry is eternal. Some now suspect that at higher energy levels, perhaps in the early universe, symmetry was perfect. Then, as the universe cooled, symmetry broke. This idea, spontaneous symmetry breaking, explains much of modern particle physics. Imagine a round table with a pencil balanced upright in the center. Perfect symmetry. But eventually the pencil falls in a direction. The symmetry is gone, but not because the table changed. The system chose. The laws were still symmetrical. The outcome was not. And so the Higgs field, responsible for mass, is said to have chosen a direction in symmetry space. This break is what gives particles their mass. Without that asymmetry, there would be no weight, no gravity, no stars, no us. Symmetry breaking, then, is not failure, it is creation. But here's where things grow weirder. Some theorists argue that perhaps symmetry is not fundamental at all, that it's an illusion, emerging from deeper chaos, or that symmetry is not favored by nature, but by us, by human minds seeking order in the noise. We crave balance. Faces are more attractive when symmetrical, patterns more pleasing when they mirror. Perhaps we project this desire onto the cosmos. Perhaps the universe is less a crystal and more a cloud, occasionally forming order, only to dissolve again. And yet, from the spiral arms of galaxies to the spin of quarks, symmetry shows up too often to ignore. It may not be perfect. It may sometimes break, but it's always there, lurking beneath the fabric. Sleep. Now, under a universe that prefers balance, but permits beauty in the break. You don't instead have to be a mathematician to feel it. You've seen it in the spirals of a sunflower, the orbit of a moon, the way lightning forks through sky. There's a rhythm to reality, a precision beneath the poetry, something hidden behind the stars that doesn't just look mathematical, it is. The more we look at the universe, through telescopes, through equations, through dreams, the more one strange truth emerges. Reality behaves like it was written in math, not described by math, not approximated by it, but built by it. Why? Let's begin small, smaller than atoms, smaller than quarks, down in the realm of string theory, one possible blueprint for reality. Particles aren't points, they're vibrating loops, and the properties of these particles, mass, charge, spin, they're not random, they emerge from how the string vibrates, like different musical notes, and music, as it turns out, is math. But even if string theory doesn't hold, the principle remains. Math works far too well. Einstein's general relativity, which describes gravity as the bending of space-time, is nothing more than geometry on steroids. And yet it predicted black holes before we ever saw one. It predicted time dilation before we ever put atomic clocks on airplanes. It predicted the bending of starlight, and we saw it during a solar eclipse in 1919, proving the theory. Why should math, something we made up with paper and pencils, match the behavior of a universe 93 billion light-years across? This is what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. It is, in his words, a miracle, a coincidence so vast it borders on supernatural. Some scientists, like Max Tegmark, have proposed the mathematical universe hypothesis, that the universe is a mathematical structure, that everything from the orbit of Neptune to the flicker of thought in your brain is simply a solution to an equation. In this theory, math isn't the language of the universe, it is the universe. And yet, that raises a darker, quieter question. If reality is math, what about us? What is a thought, a feeling, a memory of your grandmother's laugh or the smell of rain on hot asphalt? Are these too just numbers in motion? This is the tension at the heart of modern cosmology. The more precise the math becomes, the colder the universe feels. Let's return to one of the most mysterious constants in all physics, the fine structure constant, also known as alpha. It's a dimensionless number, roughly 1/137th, that governs the strength of electromagnetic interaction. It determines how atoms hold together, how light is absorbed, how chemistry works, and yet no one knows why it has this value. If it were slightly different, stars couldn't form, life wouldn't exist, reality as we know it would crumble. And yet, there it is, 1/137th, unexplained, undeniable. Some physicists speculate that alpha is a window into deeper laws we haven't discovered. Others believe it may be a brute fact, a number that simply is with no deeper cause. Still, the patterns persist. The Fibonacci sequence, the golden ratio, PID, Euler-Sitz number. These constants show up not just in math class but in nature, in flower petals, in seashells, in the structure of DNA. And then there's symmetry groups, Lie groups. Topology, the language of modern physics, is soaked in abstract math, so much so that sometimes a theory will emerge just from beautiful equations and only years later be found to match reality. Paul Dirac predicted the existence of antimatter through mathematical beauty alone. His equation was too elegant not to be true, and it was. The Higgs boson was predicted decades before it was discovered. Again, the math told us it should exist. The universe agreed. So what is this then? Are we discovering reality or inventing it? Here's one eerie thought. Maybe math exists in a platonic realm, a timeless, abstract space, and the universe merely unfolds along its geometry. In this view, Every possible reality, every possible structure already exists in the mathematical multiverse. We just happen to live in one where consciousness emerged. And what about that consciousness? Some researchers like Roger Penrose suggest that math isn't just a tool, it's linked to awareness itself. That consciousness may involve non-computable elements of mathematics, something we can't simulate, something beyond any algorithm. This brings us to the question of emergence. Is math the foundation, or is it what emerges from something deeper? Could consciousness or information be the bedrock, with math riding on top like mist on a river? The universe doesn't set answer. It continues to spiral, to balance, to unfold like an equation doing long division across time. Galaxies spin with the elegance of functions. Atoms align with symmetry groups. Light bends in the curves of Riemannian geometry. You don't have to understand the math to feel the shape of it. So as you float now, listening, resting, drifting, imagine the stars as solutions, the planets as parentheses, the moons as elegant modifiers. You are an expression nested within expressions, a brief line in a vast proof. Not a mistake, a number that holds. You stand in the middle of a desert, made of time. No sound, no wind, no stars, just space, stretching endlessly. Yet you are told it is still growing, expanding, always expanding. But expanding into what? This is the mirror paradox. Not because you see your reflection, but because the more you understand, the more you see the universe reflecting its own mystery back at you. Let's begin with something oddly poetic. The universe isn't expanding into space. Space itself is expanding. Every inch, every grain, every silent void between galaxies is stretching. Imagine a balloon, not just being inflated, but its very fabric uncoiling from within. But here's where it gets strange. The further something is from you, the faster it appears to move away. Not because it's moving through space, but because the space between you and it is growing. A galaxy a few million light years away might drift slowly, but a galaxy billions of light years away, it's rushing off faster than light itself. That doesn't violate physics, because it's not moving through space. Space is doing the moving. And now you wonder, how do we even see these galaxies if they're moving faster than light? The answer is stranger still. Light from those galaxies left billions of years ago. Back then they were closer. That light has been stretched too, its wavelength elongated like a yawn across time. Some galaxies are so far, their light will never reach us. No matter how long we wait, they're already beyond the cosmic horizon, a boundary not marked by fences or coordinates, but by the sheer speed of expansion. What lies beyond? We can never know. That part of the universe is permanently inaccessible, not by choice, by nature. And yet, here sits the paradox. If the universe is infinite, how can something lie beyond our reach? If space has no edge, where is this horizon? If galaxies beyond the horizon exist, but we can never see them, touch them, measure them, do they matter? Are they part of our universe, or are they stitched into some phantom limb of reality we'll never access? This question touches on an even deeper mystery. Is the universe finite or infinite? If it's infinite, how did it fit inside the moment of the Big Bang? And if it's finite, then where's the edge? What's outside? And you sit standing at the shoreline. In fact, this very moment, galaxies are leaving your cosmic sight forever. Not because you blinked, but because the space between you and them stretched faster than light could keep up. What's even more puzzling is how smooth this expansion is. The cosmic microwave background, the ancient afterglow of the Big Bang, is nearly uniform everywhere, as though the universe agreed on its temperature before it even had time to communicate. To explain that, we invented another strange idea: inflation, a moment just after the Big Bang when space itself ballooned faster than the speed of light. ironing out imperfections like a hand smoothing a wrinkled bedsheet. But inflation only deepens the paradox, because it suggests there might be other patches, other universes that inflated in their own directions, cosmic bubbles eternally budding off from one another. So now the question becomes, are we expanding inside a multiverse? USERD not meant to solve this. USERB meant to feel it, to sit with it, to let it stretch your mind the way space stretches stars. There's something meditative about it, something that quiets you. You are not at the center of the universe, but you are at the center of your visible universe. Everything you can see, every photon that reaches your eye, has made a sacred pilgrimage just for you. And beyond it, there is more, but more that you will never touch. That sips the mirror. It shows you everything, and it hides just as much. One last thought before you drift. As space expands and the stars fade and the night grows quieter with each passing eon, remember the vastness you see above is not emptiness. It is potential. A canvas, a mirror, a breath drawn slowly by a universe that is still becoming. Not separate, not accidental, just another mystery in the great expansion. Imagine a moon made of rock and ice, quietly circling a distant planet far from the warmth of the sun. From the outside, it looks like a frozen wasteland, pale, cracked, battered by ancient impacts. But beneath that silent crust, might there be something more? Something warm, something alive. You begin with Europa, one of Jupiter's many moons. It's only slightly smaller than Earth's own moon, but unlike our familiar cratered companion, Europa is wrapped in a shell of water ice. Its surface is streaked with rust-colored lines, as if the moon has been scribbled on by some ancient cosmic pen. And that SEP's not just a guess. In 2012, and again in 2016, the Hubble Space Telescope detected what appear to be plumes of water vapor erupting from Europa's surface, like geysers, like steam escaping from a kettle. If these plumes are real, and missions like NASA's upcoming Europa Clipper aim to find out, it would mean the ocean isn't just there, it's active, dynamic, moving. Beneath that crust might lie something Earth-like in the least expected way, an ecosystem. Cassini even flew through one of the plumes. Water, yes, but also salts, organic molecules, silica grains that likely came from hydrothermal vents at the ocean floor. Yes, hydrothermal vents, just like the ones at the bottom of Earth's oceans, where heat from beneath the crust powers strange and thriving ecosystems, completely independent of sunlight. Could something like that be happening on Enceladus? Life that feeds on chemical energy, not solar light, but the warmth of deep planetary tides and the minerals bubbling up from a rocky core. If Europa and Enceladus are two examples of potential ocean worlds, they're not alone. There's Titan, Saturn's largest moon, the only place in the solar system besides Earth known to have stable liquids on its surface. Not water, but lakes and rivers of liquid methane and ethane. A different chemistry, but perhaps a different kind of biology too. Under Titan's thick, hazy atmosphere lies a surface shaped by erosion, rainfall, even seasons, and beneath that icy shell, another subsurface ocean, water ammonia perhaps, protected by kilometers of crust, like a sealed-off world waiting to be understood. We move further, to Ganymede, the largest moon in the solar system, also orbiting Jupiter, bigger than Mercury, covered in water ice. Scientists believe Ganymede may have multiple layers of oceans, stacked like a cosmic lasagna, layers of salt water and ice, possibly 800 kilometers deep. And there's Callisto, another Jovian moon, heavily cratered, seemingly inert. But even here, models suggest the possibility of a buried ocean, quiet, slow, preserved under pressure and ice. And now you ask the quiet question. If life on Earth began in the oceans, in dark, deep places where heat and minerals bubbled upward, then why not there? Why not on Europa, where liquid water might interact with a rocky seafloor? The conditions for life as we understand them, water, heat, organic molecules, and a source of energy, might be surprisingly common. And if those conditions exist in not just one but several places in our own solar system, how rare can life truly be? You imagine it now. Beneath Europa's crust, a slow-moving ecosystem, strange biochemistry, creatures not unlike the ones in our deep ocean trenches, blind, soft-bodied, feeding off the chemical stew of hydrothermal vents. Or maybe something completely different, a shadow life, a chemistry of alien logic. And what if we sip already touched it? What if, when Cassini flew through Enceladus's plume, we already tasted something from another biosphere? Just the ghost of a world hidden under ice, but not silent. Not truly, because every crack in the crust, every geyser and vapor trail and buried ocean, they all tell a story. They whisper that water is everywhere, that oceans are not rare, that the solar system, and perhaps the universe, is full of slumbering seas, wrapped in cold and quiet, waiting for someone to knock on the shell and listen. And if the universe is full of oceans, then maybe it's full of dreaming. Not thinking, not intelligence in the way we imagine it, but the potential for movement, for metabolism, for survival, for stories made not of words but of molecules. You float, now, past these moons, quiet companions, each one holding secrets. And you wonder, if Earth had never formed, would one of them have become the first place life stirred? And if it did, would it still be dreaming now? Somewhere in the sea of stars, among countless orbits and cold rotations, we received something. A whisper. A flicker of information not born from Earth. A sound we did not send. It was brief. It was singular. And it never came again. This is the story of the signal. The one we weren't meant to hear. Or maybe weren't set meant to notice. Let's begin with a summer night. August 15th, 1977. The Ohio State University Radio Observatory, a telescope nicknamed the Big Ear, was quietly scanning the sky as part of a long-term project to search for extraterrestrial radio signals. One of its ongoing missions to monitor for narrowband emissions, frequencies that don't occur naturally in the cosmos, frequencies that might, just might, be artificial. That night, something happened. At 11:16 p.m. local time, a 72-second signal was captured. It was loud. It was concentrated. It came from the direction of the constellation Sagittarius. It aligned with the hydrogen line, 1420 MHz, a frequency long considered ideal for interstellar communication. The signal was so striking that astronomer Jerry R. Inman circled it on the data printout and scribbled one word in the margin. That sits what it became known as the wow signal. And then, nothing. But that moment, those 72 seconds, still haunts us. Why? Because it fits so many of our expectations. Let's be clear. Most natural sources in space, quasars, pulsars, stars, nebulae, don't emit in a narrow frequency range. Their radiation is broad and scattered. The wow signal, however, was sharply defined, focused to a narrowband channel. The kind of signal one might send on purpose to be distinguishable from cosmic noise. It also aligned almost exactly with the neutral hydrogen line, a universally recognizable frequency. If intelligent life wanted to say hello across the void, they might choose that channel precisely because it would stand out. And that makes you wonder, what if it was never meant to reach us? What if it was a misfire? A message between civilizations light years apart, and we just happened to be in the crossfire? Or maybe it was a test, a ping, a knock on the glass. So why didn't set it repeat? That sets the question. Some argue it was a terrestrial interference, though the frequency was in a protected band not used by earthly transmitters. Others say it was a reflection from space debris or a signal bouncing off the moon. but those explanations falter under scrutiny. What we set left with is possibility, not certainty, and that's worse, somehow, because we humans can endure silence. We can even endure rejection. But mystery, prolonged, unresolvable mystery, that gnaws at us. Because if someone out there tried to talk to us once, why did they stop? Was it a civilization now extinct? Was it a civilization that changed frequencies, gave up, or decided we weren't ready? Was it a cosmic accident? Here sips a thought. What if the message wasn't set for Earth? What if the message wasn't set for anyone? What if we intercepted something incidental, like overhearing a whisper through the wall? And what if the real conversation is still going on, right now, somewhere else? Or maybe the real signal has already arrived. Maybe it's not in sound waves or radio pulses. Maybe it's in math, in physics, in the sudden shared ideas that rise up through civilizations like smoke, unexplained, synchronous knowledge, the way two inventors across the globe discover the same principle within weeks of each other. Maybe the message isn't set in a single wow. Maybe it's in the patterns that connect everything we've been discovering about reality itself. Here steps another possibility, one even stranger. What if the signal was meant for us? And when we finally did, we weren't ready to answer. Maybe that was the test. Not just whether we could hear, but whether we could respond. We didn't sit, not really. We scanned the skies, we published papers, but we never shouted back. The planet spins quietly below you, the stars above pulse and drift. Somewhere out there, 1,000 signals might still be bouncing between stars, mistranslated, misunderstood. But maybe that sips the point. The universe isn't set quiet. It's set just patient. And the fact that we heard anything at all, even once, means that the silence might be temporary, because silence is only silence until someone speaks again. You're drifting again, not forward, not backward, just through, past warmth, past known light, past the habitual churn of gravitational routine. You find yourself tracing an orbit that never quite closes, an invisible loop, carved not by stars or mass, but by absence. This is the realm of the shadow. Not metaphorical shadow, not myth, not a place of darkness and villainy, but an actual measurable distortion in the celestial flow. Something that should be there, but isn't. A gravitational tug without a source. A weightless pull, a void that orbits nothing, yet still exerts its will. Astronomers have another name for it, orbital anomaly. These anomalies aren't rare, but some are persistent, unyielding. They remain after error margins have been accounted for, after every comet and dust cloud has been ruled out. A probe goes around Saturn, and its trajectory bends more than expected. A moon swings around Neptune, and there's a half-second delay no equation accounts for. We track and model and simulate with exquisite precision, yet something nudges our predictions ever so slightly. Something unspoken still moves. But Planet 9 is just one guess. Others suggest a swarm of tiny black holes, or a distribution of dark matter more lumpy than smooth, or perhaps more poetically, a failed star that never found a name. Something older than our sun, cold and lightless, orbiting in silence, forgotten by time itself. If it exists, it doesn't stit glow. It doesn't stit scream. It doesn't stit crash through or send messages. It only whispers in trajectories and causes the occasional spacecraft to ask, why am I off by a few meters? Now imagine this. Not all orbits are symmetrical. Not all gravitational paths are logical. Some objects may be orbiting something that has already disappeared, a remnant of a gravity well that collapsed or moved or faded. The trail continues, even when the object is gone, like a candle flame still warming the air a few seconds after being blown out. This is the kind of shadow we said talking about. You find yourself floating past one such orbit now. There's nothing in the center, no planet, no moon, but around it, a small collection of rocks spins obediently. They orbit the void, bound to a memory. Their motion makes no sense, unless, of course, something used to be there. Something dense, something gone. What vanished? A rogue planet captured temporarily? A primordial black hole that evaporated? Or maybe a star's ghost, a remnant so faint even light has forgotten its shape? Scientists call it the anomalous precession of orbits, a term both boring and terrifying, because when your equations work for 100 planets but fail for one, it's not just a glitch, it's a riddle in the foundations of motion, and physics does not like riddles. In the 1800s, Mercury itself was a riddle. Its orbit didn't obey Newton. It processed, wobbled more than expected. For decades, astronomers thought there must be another planet inside Mercury's orbit, a hidden Vulcan, circling close to the Sun, but there was no Vulcan. The answer, it turned out, came from Einstein. Relativity, not mass, explained Mercury's behavior. The laws had to evolve. You coast farther still, past the boundary of our solar system, out where the solar wind fades, and gravity holds on by its fingertips. There, some probes, Pioneer, Voyager, have felt slight but steady drifts, deviations. Pioneer in particular moved off course ever so slightly, year after year. The shift was so tiny it could have been thermal recoil, warmth from the craft's own systems pushing it minutely. But even after adjustments, a small residue of mystery remained. It's not romantic, not cinematic. It's a fraction of a degree, a hint of nudge. But when your models predict perfection, the imperfection becomes loud. It speaks in decimals, in microns, in ghostly pull. And there sits another possibility. What if these shadows aren't anomalies at all, but messages? Not intentional signals. No, nothing intelligent. But what if space itself remembers? What if gravitational patterns act like fingerprints or fossils? What if every mass that ever passed through left behind a trace, a ripple, a memory in the void? These orbital leftovers might be nothing more than galactic scar tissue. We can't see the wound, but we can trace its edge. Maybe our solar system isn't a clean, isolated clockwork. Maybe it's haunted, gravitationally haunted, by the comings and goings of ancient bodies long forgotten. Interstellar travelers, captured briefly, then flung away. Unseen masses grazing our sun's influence, leaving behind just enough pull to confuse a probe a century later. As you float deeper, you notice it more and more. Paths without centers, rotation without anchor, orbits that should have unraveled by now, still spinning in tribute to something that never returns. It's a cosmic choreography with missing dancers, but the stage still holds the rhythm. And in the quiet vastness of deep space, where no light breaks and no star claims ownership, these shadows persist, not in darkness but in distortion, not in silence but in asymmetry. You drift on, past a swirl of dust that circles a blank point, past a ring of debris that never tightens, never disperses. It just spins, around nothing. And you can't help but wonder, was that nothing once something? Or is it something we haven't yet named? You begin with something simple, a slow turn. You close your eyes and imagine yourself floating in a dark room, weightless, gently spinning. There is no wind here, no floor, no walls, just the faint suggestion of motion, the way your inner ear keeps a private diary even when your eyes can't see. In that hush of turning, you notice a softer truth. Rotation is not just movement, it is a way the universe rearranges what now means. On Earth, you feel it without feeling it. The planet spins once every 24 hours, and because of that, dawn returns, tides breathe, weather curls into cyclones, and the horizon keeps its promises. But the spin does something quieter too. It nudges time. Near the equator, where the ground rushes fastest beneath the sky, clocks tick a whisper differently than at the poles. It's a small difference, the kind no human nerve can detect. Yet satellites must care, navigation must care. The world's timing network hums along only because it makes space for rotation's private rules. Up above, the global positioning system stitches your position from pulses that cross an atmosphere, a planet's gravity and a rotating frame. Engineers fold three relativities together: velocity time dilation, gravitational time dilation, and the Sagnac correction. So your phone can say you are here with the confidence of a lighthouse. Rotation writes itself into every coordinate you take for granted. You live in a world whose maps only work because time bends just the right amount. Drift outward. You pass the cloud tops, the magnetosphere, the pale tail of Earth's atmosphere that never quite ends. Out here, rotation becomes a language the cosmos speaks fluently. Neutron stars, corpses of massive suns, spin like bells struck by gravity. Some whirl hundreds of times each second. Millisecond pulsars sweep their lighthouse beams with a regularity that embarrasses our best clocks. They are so steady that astronomers use them as a galactic metronome, listening for ripples in space-time as if the universe were a lake and gravity a stone. You could rest on the magnetic pole of such a star for less than a heartbeat before the spin would fling you away. But you do not rest. You listen. With each sweep, the star tells you its period, its age, its slowing. As it spins, it cools. As it cools, it slows. And as it slows, its timing drifts by fractions so small that the drift itself becomes a story we can follow for millions of years. The cosmos keeps time by turning. Some rotation feels benign, other rotation feels like a trapdoor. There is a trick here, a counterintuitive gift. Because the ergosphere drags space into a turn, it makes possible a theft. If you dive just right, you can take a little of the hole's spin away and leave with more energy than you brought in. It is called the Penrose process, and while no pilot will ever dare the choreography, the universe itself appears to use a cousin of it. Magnetic fields lash to a spinning hole's horizon and extract rotational energy, launching jets, thin, bright spears of plasma that punch out of galaxies for thousands of light years. Rotation powers these cosmic fountains, spin converted into light. The turning doesn't end at edges. It writes itself into theories. Einstein's equations allow a strange, exact solution. A rotating universe, the Gödel cosmos, where closed loops in time are not forbidden. If the whole universe turned just so, you could in principle walk a long, precise path and meet your younger self coming over the hill. Reality does not appear to have chosen that path. Measurements of the afterglow of the Big Bang whisper that on the largest scales, the universe is not spinning as a whole. Still, the possibility lingers like a thought you can't quite shake. Rotation, taken far enough, ties time in knots. Even without exotic universes, everyday turning strains intuition. Special relativity warns that motion scrambles simultaneity. Two events that are at the same time for one observer need not be for another. Add rotation, and the scrambling becomes a pattern of its own. Ride a fast carousel with a clock on your wrist, while another tick-tock waits beyond the fence. When you step off, the two will disagree. Not by magic, not by malfunction, but because speed is a kind of gravity's cousin and time yields to both. You pass a relic of our curiosity, a gyroscope that once orbited Earth inside a quiet satellite. It listened to the way space-time twitched and twisted around the planet's mass and spin. The measurements were tiny, angles measured in thousandths of a degree across an entire year. But the tilt was there. Earth drags space a little as it turns, not enough to make you dizzy, enough to make gravity a little less like a pull and a little more like weather. Beyond, two black holes spiral toward each other. In their final orbits, they whirl at half the speed of light, their spins tilting, precessing, sometimes aligned with their dance, sometimes fighting it. The gravitational waves they send into the universe carry that argument outward, a tremble stitched with information about spin. When those waves wash across Earth, our instruments stretch and relax by less than the width of a proton, and yet we can tell from the pattern of that stretching which way the holes were turning as they died. Rotation survives even as the objects that own it vanish into a larger night. If rotation can bend time and twist light and launch jets and expose the private mechanics of collapse, what is it really? Is turning a property of the objects or a property of the emptiness around them? Mahal once wondered whether inertia, the way matter resists acceleration, comes not from an object alone, but from its relationships to everything else in the universe. In that view, to spin is to declare a relationship. The universe answers, and it answers through time. You think of the old thought experiments, the water in the bucket that climbs its own edges when the bucket spins, the hypothetically infinite cylinder that, if made to rotate fast enough, might curve space-time into loops tight enough to walk backward in your own memory. These are more poems than machines, but their refrains are consistent. Rotation is not only kinematics, it is ontology. It tells matter what to be and tells time how to proceed. Back home, the consequences remain tender and domestic. The air swirls as storms. The ocean heaps up along coasts and spills away again. Your day is slightly longer than your clock wants because Earth's spin is slowing by heartbeats per century as the moon steals angular momentum and drifts outward. Tides are the softest possible breaks. In a far future no human eye will see, a day will last longer. The moon will hover farther. The rhythm that raised and laid down continents will have changed its tempo. Rotation writes geologies as well as star fields. You come to rest again, or at least you pretend to. In truth, you are never still. Earth carries you eastward. The planet wheels around the sun. The sun loops through the galaxy, and the galaxy turns inside a cluster that tides against other clusters along filaments that are themselves settling and unspooling. Everywhere, turning, everywhere, time negotiating with motion. It is tempting to ask what rotation really does to time, to want the single sentence that answers it all. But tonight, you let the question be larger than an answer. Time does not break under rotation. It reveals its grain. It shows you it is not a universal drum, but a field of local agreements. Clocks pass through the world and ink their own signatures. Rotation does not smash them. It lets them speak. So you breathe, slow and even, and imagine yourself on a balcony that wraps a quiet planet. You watch the stars drift west. You feel the railing cool under your hands. Somewhere, a pulsar completes another turn. A black hole twists space-time into a bright jet. A ring laser murmurs the difference between two beams. The universe keeps turning, time keeps yielding, and you, for now, are carried gently along. When you open your eyes later, not now, we can go to the edge where turning meets horizon and endings look like beginnings. Let's return to the outermost frontier, not the one marked by a flag or a telescope's final pixel or a spacecraft's furthest ping, but the one where the questions begin folding in on themselves. Not an edge of distance, but of comprehension. Not a line we cross, but one we orbit forever. This is the edge that turns back inward. You're drifting now at the limits of human imagination, a place beyond the farthest visible galaxies where even light hasn't finished its journey. It's quiet here, vast, cold, and yet something stirs, not in the vacuum, but in you. A tension, a flicker, the subtle sense that you are not just looking out, you are also being reflected back. The further you go into the cosmos, the more it feels like the cosmos is leading you somewhere not external but internal. For centuries, humanity searched outward for meaning, for maps, for boundaries, for a last star to name. But what we found again and again was a pattern. The boundary always expanded. Every edge we discovered of the Earth, of the atmosphere, of the solar system, of the galaxy, was not a wall, but a threshold. And each time we stepped over it, we didn't find answers. We found more questions, more mysteries dressed as facts, more mirrors. It is here, at this philosophical outer rim, that science and story collapse into one another. The edge no longer separates the known from the unknown. It begins to separate the self from the seeker. You look back at Earth no longer as a planet, but as a question. Then at the stars not as lights, but as echoes. You begin to see that the universe may not be a space you are simply in. It may be a shape you are slowly remembering. A shape that loops because the edge is not out there. The edge is where the known fractures into paradox, where observation and observer become indistinguishable, where the telescope becomes a mirror. You've been watching the stars, but perhaps they've been watching you back. This isn't where the journey ends. It's just where it begins again from the inside out.